Welcome. Lecture number 2 will continue the overview presentation. As I hope you had a chance to look at the slides, the full presentation was uploaded in Moodle yesterday. At least had a chance to look at the slides that we covered in the class. There is a certain pattern how we are trying to cover, a little bit new, little bit old, looking at mixing it up, making sure that we connect to what you have already studied in digital communications. So we'll continue the presentation, but interrupting it here and there for some discussion points. So let me start with a slide that I believe is a good recap of what we have discussed yesterday. So this is a pictorial representation of the evolution of the wireless systems. Maxwell, of course, the father of electromagnetic theory, the foundations for wireless communication, but J.C. Bose preceding Marconi's work, the first digital cellular systems, 1991, you probably remember it from the presentation yesterday, then came along Wi-Fi, then Bluetooth, then 3G, and then the rest of it. So much of the exciting work in cellular and wireless has happened in the last 25 years. So interesting aspect that we can keep in mind. The key points that we had mentioned yesterday in the discussion was that our course is going to focus on our understanding of the wireless, making sure that we have a good analytical understanding as well as a physical understanding and intuition. So all three elements. So the points to remember is multipath propagation, the fact that these paths will cause a fluctuation of the signal. From a representation, physical interpretation, it's a spatio-temporal process. But from a analytical tool, it just says that we think of communications as something that happens as a function of time. This is a channel that is varying as a function of time, but actually it is a spatio-temporal phenomenon. What we observe is the impact on the time scale. Then we also talked about the fact that these multipath components could come delayed in time, that causes intersymbol interference, and the fact that if you are moving, then the entire thing is changing. Your received signal is changing, the multipath components are changing. So this becomes part of the challenge that we have. Now to add to that, we also have interference, two types of interference, inter-cell interference. Somebody from another cell who's using the same frequency resources, this person is not orthogonal. In fact, they are perfectly correlated in terms of their resource. The other one is those who are within your own cell who are supposed to be orthogonal, but who have, for one reason or the other, have lost orthogonality and therefore are causing interference. So intercell, intracell interference is also a phenomenon that we have to deal with. So let me give you something to think about as we look at this. So this is what we represent as an AWGN channel. What I transmit is S of t. What I receive is S of t plus a noise, and the level of the noise determines what is my signal to noise ratio, what's the probability that I will get a symbol error. Now the introduction of fading, let's call that as a channel which is R2 of t, says that the AWGN is still present, haven't done anything with that. Transmitted signal S of t now gets scaled by a factor alpha. Okay, and this alpha can be sometimes greater than 1, which is a good thing. You get better signal to noise ratio, but most of the time you are worried about the scenarios when alpha is less than 1, and some cases significantly less than 1, causing you to have very poor signal to noise ratio. Now given that we are talking about a spatio-temporal process where the receiver can be moving, then we say that this is actually a function of time. So as you move around, so basically it becomes a time varying channel where your signal strength is constantly fluctuating and therefore causing disturbance to the communication. Now how do we capture the fact that you can have multipath, the fact that you can have the desired signal plus some versions of the delayed versions of the signal. So fading and ISI, if we were to capture it, that would become alpha naught t, which is your basic signal. then eta of t, which is your AWGN, and then the different ISI terms. This is the intersymbol interference caused by multipath components that are coming delayed in time. Okay. Now that is one type of interference. Let us say that there is no intersymbol interference. I only have the impact of the other sources of interference, co-channel interference, or the fact that I could have or intracell interference. So how would we capture that? So basically this is a representation which says that my received signal is desired signal which is fluctuating because of the fading phenomenon that is happening, plus I have an interfering signal I of t. Now I of t also is a receiver, is a signal that whose origin is not fixed, so therefore you can visualize it as a weighting function which is beta 1, let me call it as I1, this is one interferer, plus the AWGN. So this is my interference term, and whether it comes from co-channel intercell does not matter. This is some form of interference which is disturbing my signal. Okay. So I hope you see that the characterization of the intersymbol interference, the characterization of the interference which is coming from other users, not from your own signal but from other signals, can also be captured in this form. So what I would like you to do is a task. The task is, let us take the case where we have interference, generate interference from k interferers. That is very straightforward. It will now be a summation in the interference term. You will have beta 1 to beta k and I1 to Ik, that will give you the interference. Now the second element, which hopefully is something that you may have to think about, is think of desired signal plus k interferers, desired signal plus k interferers. Now each of them are passing through a dispersive channel. Okay. So for the desired signal I have L taps of intersymbol interference, and for each of these k interferers there are L1, L2 up to Lk paths of ISI. Please capture all of this into a single equation. That means received signal is desired signal plus L taps of ISI, k interferers, each of them are time dispersed, so there are different multiple path components, and you have AWGN. So in a nutshell, that is the channel that we have to work with. So as we go along, we will ask the questions: how do I get rid of ISI? How do I get rid of interference? And combine all of this together is the ability to design and build a very robust wireless system. Any questions? Any questions? Feel free to ask, because again I just have to make sure that whatever I have written is easily legible for you, if there is any doubts. So now I would like to go back to our earlier discussion and pick it up from there. The design of a wireless communication system which we are familiar with. I just want to build on our understanding of the aspects of a link budget. Okay, so the link budget in essence tells you how much transmit power you should use to have a certain signal to noise ratio at the receiver. I want to sort of quickly run through. The details will be covered in a subsequent lecture discussion. This is more of a conceptual explanation. So thermal noise floor. This is what is based on the electronic noise. This has something you don't have any control over. What is the thermal noise dependent on? Dependent on the Boltzmann's constant, the ambient temperature, and the bandwidth of the receive filter that you have used. So it is KTB. So maybe if you can write it down, the thermal noise floor is based on KTB, and the numbers that you see in the chart, I hope you will be able to verify. We will give you the reference values for the Boltzmann's constant. Ambient temperature is taken as 300 Kelvin, and you can do the calculation and verify that you will come out with a number using a bandwidth of 180 kilohertz. You should get 121.4 minus 121.4 dBm. Okay, there is a conversion from dBW to dBm. I'm assuming that all communications engineers know how to do that. It's just a factor of 30 that has to be added to make it into dBm. Now that is really not the point that we are interested in. We are interested in is what is the signal level that you must receive in order to be able to have error free or as close to error free transmission as possible. That is called receiver sensitivity. The difference between the thermal noise floor, which is a constant that you don't have any control over, to what is the receiver sensitivity is controlled by two parameters. One is the noise figure of the receiver that you are using. The poorer the noise figure, that means more noise is being added by your receiver's electronics, so therefore you have to have higher received signal power. So the noise figure, usually a term that is represented in dB, is in this case assumed to be 5 dB. It's a fairly good receiver. A poor receiver would have noise figure of maybe 9 or 10. A noise figure of 5 is considered good. Noise figure of 2 would be even better. Most commercial receivers would be in the 5 to 8 range noise figure in dB. So the noise figure, the noise floor time plus the noise figure, remember we are doing it all in decibels, so therefore it's a multiplicative factor in the expression, but in the decibel scale it becomes an additive factor, and then that is your noise level. Now from there you must have the minimum signal to noise ratio that you need. So if your modulation scheme says you need 7 dB signal to noise ratio, it is whatever is the noise level plus 7 dB. So noise floor plus noise figure plus EB by naught, required EB by naught, gives you the receiver sensitivity, and that's a very, very important number. In digital communications we may not even pay attention to it because we are interested only in BER and EB by naught, but when you build a system, the first parameter that a engineer will ask is what's the receiver sensitivity, because you can only design your cell size such that you're making sure that the majority of the receivers can receive the transmitted signal from the base station at or better than minus 109.4, this in this particular example. Now in digital communications, the way we would have done it is up to this point is good. Then the only other thing that we will have to account for is path loss, because you transmit with a certain power, there is propagation through the wireless medium, then that comes down to, so that would be a somewhat simpler link budget. Now what is different in the context of a wireless system? If I designed it like that, basically the receiver sensitivity plus path loss, that is my transmit power, what would happen? The problem that I would run into is if there was no fading, everything would be fine. The minute I have fading, what will happen? The signal will drop below the threshold, I will start getting errors. So what do wireless systems designers do? They say you have to have margin, a buffer. So which say that okay, I need to have some buffer for fast fading. Basically as you are moving, signal will fluctuate, you need to have a buffer for that. Now in addition to that, the user may go inside a building, into a basement, into an elevator, so many things where the signal level itself will drop. That's called shadowing. That means it's not because of fading, it's because you have obstructions between you and the transmitter. So that is called shadowing. So basically there are two margins that are used. One is fast fading margin, usually so L subscript F, shadowing is L subscript S. Typically if you could add 20 dB to your link budget, that would be ideal, very, very good, because one concrete floor is actually 10 dB of margin. But again the price that you will have to pay, if you make this 20 dB, your transmit power will increase by 20 dB, your cost of your base station is going to increase. So all operators want to keep this margin at the optimum level. What is optimum? As small as possible so that the transmit power is manageable, as big as possible so that you don't have problems due to fading or due to shadowing. So the key element in a cellular system is how much margin you have given to your subscriber. The greater the margin, the better, more satisfied your subscribers will be, because they will not see the effects of fading and they will be very happy with the coverage. The lesser the margin, the more they are going to complain, there will be dropped calls, the call quality will not be good. So this is a very, very important slide, understanding the fact that margins are a very key part of our cellular system design. and our ability to manipulate that is to work with that is very, very good. Now here is an observation. Let us say I have put in 20 dB of margin and I am in good signal conditions. My signal to noise ratio is 20 dB more than what it should be, because that is the positive effect of the margin. So there is a understanding that was quickly recognized, that the channel that you actually are experiencing sometimes can be much better than what you need because of the margins that are present. Is that a reasonable statement? Because you have put in, this is a buffer. In case you need it, it's there. But if your channel conditions is good, then you actually have more than what you need. So this was a observation that was made very, very early, but of course there's no way you can get rid of this margin, because then you will have poor performance. So there was a interesting discussion that took place, and I take you back almost to the year 1990 where this discussion is happening. This discussion is about the vocoder. Do you remember we talked about the vocoder being the digital representation of voice? Analog transmission analog transmission was using waveforms. The PCM transmission was 64 kilobits per second. Now GSM has come along. They need to pick a data rate for the vocoder. So here is a piece of information which we will validate a few minutes later. One GSM user, when you are assigned a traffic channel, you basically have a data rate of 22.8 kilobits per second. Keep that as a number for now. We'll fix it. We'll clarify it in a few minutes. Okay. Now the vocoder has got a certain source compression. Then it has got on top of that you will have to add channel coding. So what we see on the right hand side are three modes. Just illustrative examples. Mode 1, which has got the best speech quality, it takes this 22.8 kilobits per second and says I'm going to use 16 kilobits for representing the speech, 6.8 kilobits per second for the error protection. So priority for speech, small amount of error protection. Now this light blue, which is mode 3, we can think of it as a case where you said, okay, I'm going to use only 8 kilobits per second for speech, and I'm going to use 14.8 kilobits per second for the error protection. That means you're going to put more emphasis on error protection. And as all good communications engineers know, error protection is only overhead that you're adding to make sure that your information is reliably transferred. At the end of the day, what will determine the quality of the speech at the other side is how much speech rate did you have. So how much compression do you, the more you compress, the less the quality will be. So look at this particular plot. It has on the y-axis, again it's a qualitative plot, y-axis is speech quality. On the right, on the x-axis, it is your channel conditions, signal to noise ratio, or basically your carrier to noise ratio, basically how much impairment that you are having. Now when you have a lot of impairment, which mode would you want to use? 3. Because why? Because that has got the maximum error protection. So you can see that mode 3 will survive even when the channel conditions are not so good. On the other hand, mode 1, but it will only give you a certain level of quality. On the other hand, mode 1 will give you much better quality under good channel conditions, but notice that it will collapse much earlier than mode 3, and mode 2 is somewhere in between. So the big debate was, do we go for mode 1 or mode 2 or mode 3? And which mode do you think won? Mode 3. Because at the end of the day they said, look, this is a highly dynamic channel. We don't fully understand. GSM is a brand new system. We don't want users to complain saying, you know, my voice quality is not good. So we want a robust system. So at the end of the day they said we go with mode 3. But very soon everyone realized that, you know, a lot of times you are in channel conditions in which mode 1 could actually have been used, and therefore the next version, the enhancement of the cellular systems did this. They introduced something called adaptive vocoder, which basically had a lot of data rates all the way from 4.75 to 12.2. Notice that you can go down to 4.75, which means that you can have a huge amount of error protection. And the good thing is, without the user knowing, the system will determine what the channel conditions are and will automatically switch between the different modes. Robust when you have bad channel conditions, and good channel conditions, it will go to the ones that have got higher speech coding rates. So this was a concept that was seen and leveraged in the context of voice. So now when we come to packet communications, the same principles apply. So therefore the understanding is we don't have a single modulation method. It is going to be a dynamically varying modulation method where you could go from QPSK when the user is far away from you, which means that the user's signal conditions are not so good. They are probably seeing a lot of interference from other base stations because they are far away from your own base station. So this is probably a user who will have poorer channel conditions. You will give the person only a lower modulation scheme. Somebody in the middle may get slightly better 16 QAM, but then they may go into a building or shadowing effects, immediately they will be downgraded to QPSK. Or if they start moving and they move towards the base station, then you give them 16 QAM or even higher data rates. So this notion of adaptation based on channel conditions has become the underlying foundation on which the third generation, fourth and fifth will be built. So the notion that it is a dynamic channel, we have to build a system robust for the dynamic channel, and in order to take advantage when the channel conditions are good, we fully leverage our understanding of the, and keep in mind that this good channel condition may not last very long. You have to be able to switch, and of course you cannot expect the user to tell you when to switch to better or lower. It all has to be done in a very dynamic fashion, and this has become a part of the system that we have designed. So we are feeling very good because we have understood the wireless channel, we have understood why they have all these fading margins, and we look now and say, go to the handset manufacturers and say, what, without our understanding of the wireless channel, your device will not sell because people will not buy it because the channel conditions. But then our good feelings don't last very long because they show us what's inside the phone. So this is a GSM phone designed by Texas Instruments. It's a single chip phone, and I look for things that you recognize: ARM microprocessor, DSP. Okay, I see a camera interface, and I see all kinds of memory interfaces. I see LED display, keypad. I say, where is GSM? Okay, somewhere in the corner is GSM, because that's how much silicon is needed for implementing the GSM functionality or the communications functionality. What else is there? Bluetooth, infrared. So basically the phone it has got lots of functions, but the master or the queen of functions is sitting in the left hand bottom corner. That's what we are studying. So without this, the rest of it is not very useful. So still there is a role for us to play, but we are a little bit more humble, saying that it is a small part but a very important part. So what has been the evolution? It was once upon a time a single device with a single functionality, which was voice. Today it's got all kinds of functionalities, but voice happens to be one of them, but it is one where the RF connectivity is a key for us to be able to establish what we want to do. So I want to quickly move into the different generations of phones or of cellular systems, and spend a few minutes trying to remind you of what you may have already have studied in the digital communications. So multiple access, it is a shared medium, wireless, so large number of users. I have to keep them orthogonal to each other. How do I do that, and what's the best way to establish orthogonality? So first generation systems said that we will give each user different frequencies. So in a cell, each user got different frequencies. So think of it as three orthogonal axes, and I will tell you how to visualize them. X axis being frequency, Y axis being time, and Z axis being code or power. Just think of it as a third dimension, will become clearer as we move through this sequence of slides. So notice that a user is given a unique frequency. There is a separation between two users, so therefore they will not interfere with each other, and when it is each user can transmit for as much time as they want, there is no restriction, they can transmit, and they can transmit with full power, maximum power, because yellow transmitting with maximum power does not affect green or red. Each one is orthogonal in terms of frequency. So this was the first generation systems, FDMA based systems. We found that there is a lot of wastage of resources because there is guard bands between them. So second generation said we will do things a little bit differently. We will change the orthogonality from frequency to time. Okay? So everybody has the same frequency, but we will now have time slots. When it is your time slot, you can transmit with maximum power. But at that time nobody else will be transmitting because it's not their turn to transmit. So basically you get a pattern of time slots and then the pattern repeats, so you get a time slot every frame. So this turned out to be quite attractive because time we can get very precise clocks and therefore design time division multiple access systems. This was a very interesting way. This was the way we could design the systems. Now I want you to start thinking about another aspect which is very important for us, and that aspect is the aspect of equalization. So let me just sort of switch to the screen for a moment and ask you to think about the aspect of, so let us say that the delay in the channel, that means the time gap between the first and the last arriving paths is, let's call that as tau, is 5 microseconds. 5 microseconds. Now when I did FDMA, let us say that we gave each user 10 kilohertz. The bandwidth in FDMA is the first generation system, bandwidth is 10 kilohertz. What is the symbol duration if we were using binary transmission? 100 microseconds. Okay. Now if I were to ask you how much intersymbol interference is going to be between adjacent symbols. So if you were to think of one symbol like this, the next one is going to arrive like this. So the amount of intersymbol interference is very, very minimal because the 5 microseconds in 100 microseconds, the duration of the symbol is 100 microseconds, the delay between the first and second path. So it almost looks like there is no intersymbol interference. Would you agree? Anybody not clear about the symbol duration and delay spread, how it impacts each other? Okay, let's move to TDMA.
Can you repeat the last part?
Okay, let us say that the bandwidth of the signal that I am transmitting is 10 kilohertz. Binary transmission. So approximately one symbol, basically it's 10 kilobaud is my signaling rate. So basically if 10 kilobaud is my signaling rate, my symbol duration is 100 microseconds, basically reciprocal of the baud rate. So 100 microseconds will be one symbol, and the next symbol will come after that. The delayed version is going to come with a delay of 5 microseconds. So basically the intersymbol interference is going to be caused by the fact that there are two copies of the signal which are slightly overlapping with each other. Okay, but the bulk of the overlap is common. Basically the same symbol is coming on both branches. There's a little bit of the previous one. So if this is S0, this is also S0, this will be S of minus 1. There's a little bit of S minus 1 that is coming in, and therefore you have to make sure you take care of that, but you can almost choose to ignore it. You may not pay a penalty for it. Okay, TDMA. Let's take GSM. GSM, the baud rate, the symbol rate. Symbol rate is 270.833 kilobits per second. It's a binary modulation scheme. So the symbol duration is approximately 3.7 microseconds. How many symbols of intersymbol interference do I see? 3.7 is the symbol duration. There is a delay of 5 microseconds and then a copy would come. So how much ISI would I see? 2 symbols. So the number of symbols of ISI, symbols of ISI is 2 symbols. Okay, 2 to 3. Okay, depends on how the alignment occurs. You may have to worry about a third symbol in your demodulation. Okay, but it is still manageable. We can design equalizers. Okay, now if I want to increase my data rate, let us say I want to go to 10 megabits per second. Okay, this is using TDMA methods. Okay, so I want to increase, I want to have more users. So therefore, FDMA means only one user at a time. TDMA, GSM has got 8 users in a frame. I want to increase it to 10 megabits per second. Now, if I try to do that, notice my symbol duration, what does it become? 0.1 microseconds. How much of ISI will I see? Number of symbols of ISI? Number of symbols of ISI? Almost 50. It's going to be very, very difficult for you to design an equalizer for 50 symbols of intersymbol interface. It's a very complex system. So TDMA seems to have a limitation in that if I keep increasing the data rate and keep adding more and more time slots to support users or to achieve high data rates, the place where I am going to pay a penalty is going to be in the complexity of the equalization. Yes, I can maintain orthogonality in time, but the receiver is going to be more complex, so therefore I have to be careful with that. Okay, so let's keep that picture in mind. So that was second generation. We were happy with users being satisfied with 100 kilobits per second, but third generation came along. People said, no, we want the data rates, packet data should go to 14 megabits per second and higher. If you can go back and look at the slides, third generation was targeting around 14 megabits per second. So before we get to that, let's remember we said one time slot of GSM gives you 22.8 kilobits per second as the raw payload. Let's do a quick calculation to get you familiar with the TDMA concept. At the bottom of the screen, that's your GSM signaling rate, 270.833 kilobits per second. A GSM frame is divided into 8 time slots, and each time slot has got the following structure. There are 2 places where user data is sent. That's basically the payload 1 and payload 2. Each of them has got 57 symbols or 57 bits. In the middle, there is overhead. 26 bits for you to do the synchronization. There are flags which tell us whether this is user data or control information, and then there are some guard bits on either side. So at the start of the burst, and then there are 3 plus 8 and a quarter at the end of the burst. Okay, why 8 and a quarter? We will. I'll tell you sometime. There's some history to that. But basically, this is the structure. A frame has got 114 bits of payload, useful information, and the rest is overhead of one kind or the other. Okay, if you add it up, it will come to 156.25 bits. That's approximately 576 microseconds if you look at it at this data rate. Now this frame of GSM is embedded in what is called a multi-frame structure. The system counts not on the basis of individual frames, on multi-frames, and the multi-frame structure is based on a structure of 26 frames. 26 frames make a multi-frame. That's what you see at the bottom, and that is 120 milliseconds. That's a nice number. So the clock keeps track of 120 milliseconds, and so in this 26 frames, each user should have gotten 26 time slots, because each frame you should get one time slot. Now every 13th frame is used for control. So basically out of 26, only 24 will be used for user data. Again, there is a numerology involved in it, but once somebody explains it, it should be fairly straightforward. Okay. So now what is the data rate per user? I get 114 bits of payload. I get it once in 576 microseconds. So 114 bits every 576 microseconds, that is my data rate. But I don't get it all the time. I get it 1 out of 8 time slots. So there's a factor of 1 over 8 because it's a TDMA system. And I also have to set aside 2 out of 26 frames for control information, for sending some measurements. So therefore, there is a factor of 24 by 26 or 12 by 13 as the factor that all. So at the end of the day, this is what I as one user will get. 114 bits every frame, 24 out of 26 frames, 1 out of 8 time slots. Do the rough calculation, it should come out to 22.8. So what was my signaling rate? 270.833. I divided by 8, I should get some number much higher, but because of all the overheads, what I eventually get is only 22.8. It's actually a fairly well designed system. The amount of overhead is kept to a minimum. It's a very, very robust system. But this is how TDMA works. You have a raw signaling rate, you got all kinds of overheads, then you get what is the user frame, and make sure that you don't forget this 1/8 time factor, because that's what tells you that that you don't own all the time slots. Now as GSM has evolved, when people wanted to have higher data rates, one of the options was to give you more than one time slot. So if you got 2 time slots, then you could go 22.8 times 2, and then eventually you can ask for all 8 time slots. That is a possibility. Okay, so the way to get it is to ask for more time slots in a TDMA system. So that is TDMA. Complexity will be in the equalization. GSM well designed because you got only 2 to 3 symbols of ISI, but once you go to 10 megabits per second, a TDMA system will have some difficulty. So then came along a system which is based on spread spectrum technology. Spread spectrum technology says that orthogonality will not be in frequency or in time, it will be in the third dimension, which is the code or a signature sequence. These signature sequences are inherently orthogonal. So therefore, they will not interfere with each other, though you are using the same frequency and transmitting at the same time. So for example, all these 4 users can use the same frequency at the same time, but they have orthogonal signature sequences, and therefore they are don't interfere with each other. So the question that was asked yesterday is, why not add more and more users? I am keeping that, this is a good, looks like a very good way to increase. So let us see where the limitations will occur. I'm assuming most of you are familiar with the spread spectrum, but just as a concept diagram, the input data is a narrowband data. I spread or basically multiply it with a spreading sequence. In this case, I have used a 4-bit spreading sequence. So using a 4-bit spreading sequence, I have basically multiplying it. So what would have been 1 bit per second now becomes 4 chips per second. These are called chips to differentiate between what is the information input rate and the channel rate. So channel is measured in terms of chip rate. So 1 bit per second becomes 4 chips per second. So basically the bandwidth expands by a factor of 4. If you had done a factor of 16 chips per symbol, it would have spread by a factor of 16. So the controlling factor is how much spreading do you want to use. So the good thing is you can find several orthogonal sequences and therefore start using different users, orange, pink, you can keep adding those users. How does the receiver work? The receiver applies the same sequence, basically multiplies the received signal by the same sequence as the spreading sequence. So if you multiply 1 1 minus 1 minus 1 by 1 1 minus 1 minus 1 1 minus 1, it will get 4. So basically it will recover the original signal if it matches. If it does not match, it will reject it. Okay, so that is the underlying principle of a spread spectrum signal. Now what happens if there is a delay spread? Supposing you shift by 1 bit, these spreading sequences have got the property that even if you are off by 1 chip, the correlation will be very low. So intersymbol interference is sort of inherently suppressed in a spread spectrum system. So you will reject other users. You will also reject intersymbol interference, again to a limit, but the important thing is to know is how much benefit are you getting. So a simple example, this is measured in terms of processing gain in the third generation system, speech at 9.6 kilobits per second. I actually use it is through spreading, it is taken up to 3.84 mega chips per second. So the ratio of these two to a logarithm scale is 26 dB. That's the processing gain. That means that if there is a interferer who is 26 dB stronger than me, I will still survive. and still get my signal out, because I have, it's effectively like saying my signal will be amplified by 26 dB compared to everybody else. Okay, so that is the advantage. Each user is given a unique spreading code, and multiple access is through the spreading codes, and because you're using codes, it's called code division multiple access, and I'm sure most of this is known material to you. Okay, how do we generate codes? One of the simplest ways is the Walsh-Hadamard codes. If I say that I want to have spreading factor of 4, how many orthogonal codes I have is only 4. If I go to 8 and then to 16, I will get whatever is the size of the matrix, that's the number of codes. I can of course go to quasi orthogonal codes, but at some point I will run out of the spreading sequences. So this is where the limit has been. So CDMA 2000, if you had used a CDMA phone, was using a spreading factor of 64. So theoretically, you could use 64 users in a particular cell, you could give them all and they would not interfere with each other. In practice, it was found that you could use anywhere up to 30 to 32 user codes. After that, because of loss of orthogonality, and I'll explain in a minute where the loss of orthogonality occurs, you started to see degradation in the performance. So basically, even if you had codes, the performance of the system may limit the amount of spreading that you could do. So now comes a very interesting challenge. 9.6 kilobits per second, I can spread by 256 and still get a system. But if I want to transmit at 10 megabits per second, let's say I want, a user says my fourth generation system is going to transmit at 10 megabits per second, and you say, well, good, I will design for you a spread spectrum system. Factor of 64 I will spread to make it very robust, to give 64 users, each of them getting 10 megabits per second. How much bandwidth do I need? 10 megabits per second, assume binary to each, so it's a 10 megahertz is what I will need if I don't spread. If I spread by a factor of 64 megahertz. And how much, all our operators put together don't have 64 megahertz, leave alone one user. So, and then you say, well, for broadband systems, maybe CDMA has got a problem because I don't have the bandwidth. Well, somebody was very smart, they said, you know what, I'm going to reduce the spreading factor. If you ask low data rate, I will give you 64 spreading. When you ask high data rate, I will give you only 4 spreading factor. Okay. So when you use less spreading factor, that means you don't have much processing gain. So where should you compensate? By transmitting more power. So what do? This is a scenario where everybody is using the same data rate. Here is a case where a CDMA system where one user is using low data rate and the green user is asking for high data rate, and because I don't want to expand my bandwidth, I am reducing his spreading factor. So therefore, I have to increase his power. Okay, looks very nice, except if there is loss of orthogonality. Loss of orthogonality means these colors mix with each other. And then what happens, the green user will wipe out everybody else because he is transmitting at very high power. So that is the problem that we see in the last line. It's very difficult to have high data rate and high spreading factor. You have to reduce the spreading factor, which means that you are going to transmit with high power, which means that the minute orthogonality is lost, therefore so when is orthogonality lost? When there is multipath. Now in a wireless system, I can never guarantee you a channel where there is no multipath. So therefore, spreading factors with CDMA, there is a challenge. So we are back to the drawing board. I want broadband systems. I don't want the complexity of equalization. I don't have a bandwidth to spread. What do I do? So we went a full circle and said, well, FDMA is probably the most robust system, provided we can get rid of those guard bands. If you get rid of the guard bands, it's very good because each of these only 10 kilohertz, ISI negligible. I can create as much bandwidth as I want without increasing complexity. There is no limit, and I can just keep adding more and more of these narrowband carriers, and that happens to be OFDM, orthogonal frequency division multiplexing. This is the mode by which we have built the 4th generation. Very likely some of the 5th generation will also be some variant of this of the OFDM system. Okay, so to summarize, CDMA, if I lose orthogonality, I have a problem. I cannot of course spread for high data rate systems, so therefore I have the issue of orthogonality which is caused by multipath. For TDMA systems, the complexity of equalization becomes a factor. OFDM is very attractive because I don't need to do equalization most of the time, because my carriers are all narrow band, my symbols in each carrier is quite long, so therefore I deal with it on a carrier by carrier basis. In addition to that, OFDM, I'm sure if you have studied it, or we will be doing it towards the end of the course, is built on the IDFT and the DFT, discrete Fourier transform. Very efficient implementation, so therefore it is a system that is very attractive from the point of view of the implementation. So then everybody should go to OFDM, right? Everybody, why should throw out TDMA, FDMA, CDMA, and then everybody should go to OFDM. So there must be a catch somewhere, there must be some price that you have to pay. It turns out to be that there is this parameter called peak to average ratio, which is the which is going to determine the efficiency of your power amplifier, and that is not very good for an OFDM system. In fact, it is much higher than a CDMA system or a TDMA system, and that is where the price we pay. You will have to generate more power to transmit at the same level as the other systems. If you have to generate more power in your handset, what is happening? Basically, if your power amplifier is operating at lower efficiency, it is being generated as heat, and if it is heat, guess who is absorbing the heat? It's you, because if it's next to your face. So basically, peak to average ratio is an important one. It's a price that we pay for OFDM, but it's got lots of advantages. So the way to think about it is, yes, take the advantages, find a solution for the peak to average power ratio challenge, and that's what we have seen in. Another very interesting phenomenon or aspect about OFDM. So think of this this figure in the lower part of the figure. You have a large number of small carriers, narrowband carriers. Let's say I have 2 users, and these 2 users are very dynamic. They are both are accessing the internet. Suddenly one person is asking for high data rate, and then is idle for some time. Then in the middle, the other person is asking. So dynamically, they are asking for different data resource requirements. So see how, if this is your time axis, at different time instances, you can allocate different number of subcarriers to each user. So basically, you dynamically change the allocation based on their current requirements. Not only that, remember the fading phenomenon. If the yellow user has got some channels which are affected by fades, you can give him some other channels which are not affected by fade. So again, you can overcome the fading aspect, you can address the dynamic need requirements, and you can also overcome the equalization issues. So again, OFDM has got some very attractive advantages. Now you may say, who discovered OFDM? Wireless guys who discovered OFDM, right? 4th generation. The answer is no. 50 years, almost 30 years before wireless was invented, they had already come up with the OFDM concept. They didn't call it OFDM, they called it multi-tone transmission. Multi-tone meaning multiple carriers. It was a different terminology. It was invented by a telephone company, the wireline telephone company, basically Bell Labs. So the notion was a wireline channel, copper, has got a large bandwidth. It's got about 4 or 5 megahertz of bandwidth. How much bandwidth do we use for transmitting voice? 4 kilohertz. It's a huge waste of resources. What happens to all the other bandwidth that you're using? Unfortunately, the gain is very poor in some of the, as you go to high frequencies. So the notion of using multi-tones, transmitting at different power levels to exploit that extra bandwidth that was there on the copper channels. So you see why it was originally designed, to take advantage of channels which did not have good gain but still get capacity out of it. And if you go back and look at all the modems that have been used, multi-tone modems, you'll find it under the family called DSL family. Digital subscriber loop. Basically, it's data rate over copper wires. So initially it was advanced digital subscriber loop, very high data rates, asymmetric digital subscriber loop, very high data rate subscriber loop. Now they just call it XDSL. So basically, very high bandwidths you can get over copper. If you have good quality copper, unfortunately India does not have good quality copper. We don't have much copper to begin with. So, but if you have good quality copper, you can get very high data rates, several megabits per second. Now that has been the starting point of OFDM, but now the wireless people have adopted it for the several advantages that it gives us, and therefore the continued development has been taken up by the wireless community. So let me just give you a introduction to 4G systems, and then we will stop there. So if I were to ask in a nutshell, I've understood multiple access. I've understood what the earliest generations did. What were some of the factors that enabled higher data rates to be achieved in the 4th generation systems? So first was OFDM, that I could divide multiple carriers and then allocate to different users and use it very dynamically. That was one. The second aspect was the introduction of multiple antennas. If you remember, I mentioned antennas can give you diversity, they can also give you capacity. Let me just give you quickly this diagram on the top right hand corner. Diversity means using both antennas to transmit the same signal, 2 copies of the signal. Multiplexing means you transmit different copies of the signal to the same user. So that means this guy gets double the data rate. But you still want to take advantage of the fact that you have 2 antennas, and therefore all the advantages of a MIMO system, multiple antennas at the transmitter, multiple antennas at the receiver, are being exploited in a 4G system. So if you have multiple antennas at the transmitter, you can do beamforming, only radiate in the direction of the user, so you can have more range. You can also radiate beams to different users, so which means that you can have support more users, or to the same user you can get more data rate. That's all the advantages. The third aspect of 4th generation systems is that traditionally wireless systems have been frequency division duplex systems. Uplink, the way you communicate to the base station is at a different frequency that the base station communicates to you. But in the 4th generation, we've also introduced the time division duplex, where you have only one channel. Part of the time you communicate to the base station, the rest of the time the base station communicates to you. So basically you have a downlink, uplink. So it goes ping pong method. So there are some advantages with this. So FDD means frequency division duplex. You have different frequencies. TDD means that you are doing on the same frequency, uplink and downlink are happening. So these are some key elements of the 4th generation. There are some more elements of 4th generation which are based on the technologies that have evolved around cellular systems, and I will pick it up from there in the next lecture. But please do read. I think at this point you should be able to cover a lot of the slides which are starting from here going on. The last part we will talk a little bit about the 5th generation systems, which will be completed in the next lecture. So thank you. We'll see you tomorrow.